Okay, good morning. Let's get started. Do you have any questions from last time? Any comments, suggestions? Yes.
Graded the first part of the project, like the part one, because I got a point off and there's no marks or anything.
We all did. So I'll explain that. So it's a major announcement for today. We graded projects last night rather liberally. And I think overall you did a really good job. Average was about 85 for a class. And there was one project with some extra credit points that exceeded 100. So we are quite pleased to see your work. And then you can pick up your graded reports from 353 Corey. If you go to the lab today, you will find your reports there. Okay. So let me just get set up here. So what we're going to do today is we're going to finish up arithmetic blocks and go into power consumption, revisit that issue now that we understand different logic styles and that we can play with more switching probability because we understand dynamic power completely. Yes.
For the exam, will the stuff in Chapter 6 about the probability
No,
stuff? No,
that's
okay.
not going to be, right? So I have a couple announcements to make today. So we'll post homework 8 on Friday, give you a little break after the midterm. I'm sure nobody is going to be eager to work on homework on Thursday, right after the exam. And it will be due Thursday the week after. Midterm 2 schedule, there will be a review session today in Northgate Hall. That's on near the Northgate, as the name suggests. The exam will be on Thursday in 101 Morgan, and there is a map on the website if you need directions how to find that building. And there will be no lecture on the exam date. The material that the exam will cover, again, will be everything that is basically covered until the last week's lectures. So all the material from midterm 1 is also a fair game, but there will be a clear emphasis on the material after midterm 1, mainly wires, logic families, logical effort, and adders. And I need to do a little voting here because I understand that my office hour is not really convenient this week because it's right couple hours before the exam. And I think it's quite unhealthy that you try to really learn the things last moment. I should give you at least 24 hours to ease your mind. So I'm thinking to shift office hours back tomorrow 9:30 till 11:30 because some people have 2:40 from 11 until 12, and I think 9 to 11 would be a little bit too early. So I'm suggesting 9:30 to 11:30. Everybody all right with that? It's better than Thursday. Okay, so I'll post that on the website today.
Is it possible for you to make it in the afternoon sometime?
Afternoon? How about 3 to 5 afternoon? Is that better? Okay, so I'll double check if everything is clear in terms of room availability, and then I will post that online. So let's plan 3 to 5 tomorrow. That sound good? So tonight, review session, and that's about it. The rest of the semester is going to be fairly involved. You'll have a midterm, then there'll be project 2 coming up soon. So I think there'll be a lot of interesting work for you. Project 1 has been graded, as I mentioned, and overall you did really good. The average is, this time we separated undergraduate and graduate students. Average for undergrads was 84, and minimum was 61, and one project got 102. And for grad student, average was around 90, minimum 76, maximum 99. And now that we realize that you are really enjoying the project, we are going to give you another one next week. And so this time, so let me talk a little bit about the main takeaway points that you should get from Project 1. So basically, the major takeaway point is if you have a circuit like this, and that is a common topology that you may find in real designs. Then oftentimes you will have to optimize the circuit to meet certain performance or energy goals. And in this particular project, your task was to find optimum sizes for these X and Y inverters, such that you have first minimum delay and then you back off from that delay, minimize power. So major takeaway point here is that for the case when you have a network such that you have imbalanced load because you have different number, this is like 2, 4, 6, then what you should learn is basically that the branching theory doesn't work for X's and does work for Y's, because when you have imbalance, you cannot assume that all the X's are equal, because in that case you will have suboptimal solution. Now it works nicely for these Y's because all of them are loaded with the same capacitance, CL, 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 and by making stage delays equal, you will turn out to have basically equal Y's for the minimum delay case. And in that case, you can safely apply this branching theory and say, now I have B times Y, B2 times Y, and B3 times Y. You can safely assume that all of these branches basically have the same size. All of these 6 Y's are the same because they are loaded with the same capacitance. But now when you break that symmetry over here, you basically have certain amount of capacitance looking into this C1 that is different from C2, different from C3, and then in that case you can no longer say this is equal to 3 times or B times X, because it doesn't work in that way. So that's important takeaway point. And then what you also have to realize is what happens in real life. These are just the first order quick estimates of what's going on, and we asked you 2 things, basically to calculate propagation delay and energy and compare them in SPICE to validate your analysis. So basically the major point that you should have realized is that if you look into signal slopes and read the background document, you will realize that they were all calibrated, that the gate was calibrated for equal input and output slopes, which means equal fan-out. So when you do some sizing and size pruning, then you basically have no longer equal fan-outs. Your fan-outs will be different. You'll have a tapered result where you have more and more fan out toward the final load, because that's where most of the energy is stored on these final stages. So what you had actually when you optimize your design, you roughly had this situation. So this guy had a fan out slope of fan out 1. This was about 3, this was about 4, and this was about fan out 9. So when you look into your delay analysis, then you see basically that these 2 guys are okay. So fan out 4 slope input is almost fan out 4. It will be very little deviation. But what I'm really after is to look into these stages over here, because that's where the most discrepancy comes in. So basically you have, if this is your fan out 9, then you have only 1/2 of that fan out slope at the input. And over here you have about 1/3. So the most discrepancy in the delay you will find from this stage and then from this stage, and this stage is then okay. So that is a full credit for your answer about the delay analysis. Most of you just said, oh, hey, there is something to do with slopes. If the signal gets faster, and then if you go through the network, it gets progressively worse. No, it doesn't really. So this stage is really the most critical, and that's what you should really understand. So it was really simple in that regard. And then for the energy calculation, so you basically were given 2 capacitances for a reason. For delay calculation purpose, you had this CD, and then for the energy calculation purpose, you had this CE, which basically also included, so this included only 0 to 50% transition, and this was basically 0 to 100%, because that was total amount of charge that you put on these capacitances and take out of supply voltage. So now this also included extra amount of work that you need to spend when both transistors are turned on, and CE was greater than CD for that reason, because you had this direct path current. And you can basically approximate that CE is approximately CD times 1 plus some factor that corresponds to that short circuit current. And then what happened in the initial case, you had this CE slightly larger than the CD. And then when you do all these optimizations, basically you have your input slope improved compared to the output slope. So there'll be less time that your device spends in short circuit mode, and then this constant will decrease a little bit, and you're expected to have slight decrease in your energy. But the energy numbers were a little bit tricky because that was too close, and depending on various ways you built your spice deck, use different waveform slopes at the very input, you got sometimes like dead-on numbers that would really match. Sometimes you get a little bit better, a little bit worse, but this is kind of what we were driving you towards to understand what's going on when you implement this in reality. So now for the project 2, what we are going to do, what you learned here is basically hand analysis and spice. Now we are going to go a step further, and we are going to give you layout so that you basically now learn another step of discrepancy. What happens when you have all these parasitics, all these wires and things? And we are still toying with the ideas, but I think one thing that we are pretty firm about is that we are going to make this a class design contest. So we will give you a certain circuit that you need to design, and there will be two sort of opposing metrics. So there will be a propagation delay, and there will be also total layout area, how tightly you can pack all that into your design, and there will be no power constraint, but that means basically area is taking care of that. So what we are going to grade you on is basically who gets the best product of propagation delay and layout area. So that's going to be the game for next project. Question?
Are those individual projects or group projects?
Group projects.
How big of groups? Do you know?
2. Again, 2. But you have slightly more time. You'll have 3 weeks. 3, 4, and 9, those are basically just the fan-out numbers. This is a fan-out of 1 because this one was 1, and it was driven by inverter that had also 1. So basically fan-out of this one is capacitance looking into here divided by input capacitance, so that is fan-out equal 1. And if this one was approximately 3 because all of these were close to 1 after the optimization, then this was around 3. Output capacitance, input capacitance looking into here divided by the input capacitance of this guy, right?
Does this explain why the value in the spice was faster?
Absolutely.
Why is it faster?
Because for you. Right, but what you assume basically, if you have, let's say this is fan out equal 3 case. So what you assume that you had fan out 3 slope over here. And then for your hand calculations, you assumed the same slope at the input. But now for your spice, you get this. So is this going to be faster? Okay. So that's the question.
So even for a simple buffer change, when we do the sizing, we do it in such a way so that means z over y is equal to y over x. So isn't that except for the first stage, all other stages, the fan in and fan out are equal?
That's for the minimum delay case, but this is for the optimized case.
Oh,
this is
optimized
basically
case.
talking about the major
Optimized
point,
case, okay.
optimized
Not
case.
for the first case.
Optimized case. Okay. All right. So I think you overall did really good on this project, and that was our goal to get you to learn these things. So let's go back to the class material. So we will wrap up with multipliers today and talk a little bit about shifters and introduce power consumption. And then if we have time, introduce sequential circuits. Oh, back to your question, Chris. So you asked about the grading of phase 1. So basically what we did for the phase 1, so we did grading of projects, and I hope you like your scores, you're not going to complain too much, but just a little explanation is good. So what we did is basically we graded, as we promised, like 3 things. One was the results. So basically that was 30%, and then results from your phase 1, 2, and 3 were all equal, like 10%. And we took basically optimal results from both Excel and MATLAB, and we allowed 10% tolerance going down and going up from the worst case variations. If you're outside that box, you automatically get 1 point off. If you're way off from that box, you get 2 points off. And that was basically the methodology. So if you look at under numbers, that's hopefully going to help you understand what's going on. So that was basically phase 1, 2, and 3, each 10 points. The second was basically the correctness, and correctness mainly meant the third phase. So in the third phase, we were also looking for about 30%. So first of all, you had to understand where is this discrepancy coming from in the hand calculations in SPICE. Second is if you provide any supporting data and say, well, I measured the delays, I measured the slopes, that's also some extra points there. And then if you clearly went after understanding and explaining what's going on, for the analysis part, you get the major points. It was about 15%. For understanding of the energy, it was about 5%. And finally, other points. If you brought up some other interesting points, you get another 5. And that was 30 points for the correctness. And finally, the 40% was for approach and for your report. So we graded basically the overall organization of your report, the clarity of your report, and depth of analysis. How much did you go into detail, and how much data you provided that is necessary to support your claim. Sometimes, for example, you had very long tables with a lot of data that wasn't really all used in text, so that wasn't really the greatest report. Or sometimes you just put, for example, some groups did put, for example, figures and absolutely no explanation what's around the figure, no X's, no captions, nothing. And that's something that you should do, basically, because that's important for the organization part. And overall, some groups did a really good job on that. Basically, went after analysis of all these slope discrepancies. They plot different plots. For example, on a linear scale for rise times, they plot all the dot points to figure out where exactly their points are and sort of try to understand that. So that was really good. So that's what we were really after in this, and that's how you should look after your grading. If you have any questions, come talk to us. Okay. So let's get back to multiplier. So this is where we stopped last time, and we analyzed this multiplier, where we have basically the strategy for the implementation of multiplier. You create a bunch of these partial products, and then you have to sum them all up. And then adder, again, appears as an important block that you need to understand what's going on in this adder. And then what we did is, and I'm going to show that hopefully better on the overhead camera, is that when you start from this parallelogram over here, you can basically say, well, I don't really care in which order I'm going to add all these bits. So what I'm going to do is push this up and create a triangular structure like this. And then what I really need to do is to understand what's the fastest way I can add all these numbers up. And I need to do that in a couple stages. So the idea overall is to try to level this off and sort of like flatten this out, push this up, because I realized that at the bit position 3, I have 4 bits to add. All other bit positions are 3, 2, or 1. So this is where I really need to spend the most effort first. So now, the question is, how do I cover this map with the fewest with the smallest hardware area, fewest number of adders, such that I can do this the most efficiently? So obviously, I have to tackle this stage first. And I know when I have half adder, that's basically 2 inputs, I'm producing sum and carry at the output. And so what is this going to collapse to is basically I'm going to have, at this bit position 3, I am going to have sum at this bit, and then the carry will go to the next stage. So carry will propagate to the next stage. Now, since I have carry here, so basically I have to clear some space so I can place this carry dot over here. And in order to do so, I need to compress this guy and provide a sum bit over here, and so I can push its own carry over here. So that's the situation that I'm doing actually in this first stage. So as a result, what I have is basically, this is my sum at bit position 3. then this guy over here at the bit position 4 produces a sum over here, and this is a carry from the bit position 3. So now what I have is this bit that was basically carry from the bit position 4. Okay, so everybody clear with this? And then in the second stage, now I need to reorganize this again. So basically what I did now is I tried to level this off, and I had 4 bits deep addition in the worst case that is now reduced to 3 bits. And now what I can do is basically cover this again using the same strategy with minimum number of adders that I need. And then I know that if I use half adder, I have 2 inputs, 2 outputs. When I use full adder, I have compression basically. I have 3 inputs, 2 input bits, and the carry in, and then I have 2 outputs. One is sum, one is carry out. So what I eventually get is, if I use half adder here, that will basically compress this one to sum at stage 2. And now what this does is basically it produces sum and carry. So basically we produce sum at stage 3, but then we have carry from the previous stage. Then we have sum at stage 4 and propagate carry from the previous stage, and so on. So we eventually get sum at stage 5. This is carry 4, and we finally place carry from the stage 5 over here. So now we further compressed this tree to only 2 levels of binary additions. And then what we need to do now is just use all these half adders for the final implementation, and we are done. So now this is really becoming useful when you have very large number of bits. This was a really simple example of a multiplier with a very small number of bits. Question?
Final adder is a full adder, half adder or full adder?
Half adder.
Because except the last one, the middle ones have to take a carry from the previous stage with ripple through. So we make a full adder instead? The bit 1, bit 2 to 6 would be full adders?
2 to 6?
Because they have to take the carrier from previous, a ripple through from previous adders.
Oh, you mean, okay, yes, that's correct. So this is basically half adder, and all these others are full adders. So this is then half adder, and these are full adders because they have to carry the carry from the previous. Yeah. Okay. Okay. And this technique is very useful for very large number of bits, for very wide operands. And this is the final implementation of this thing, basically. If we try to put this together. So here's the way you implement this. So this would be half adder here. So half adder. So this is your first stage. You have 2 of these half adders here, and they generate sum and propagate carry to the left. And then you finally do this half adder here, 3 full adders, and then you have the final addition stage, and you're done. Okay? All right, so let's go back to slides. So this is the same illustration. So now you see that much like in adders, you have similar type of optimization goals, because once again you have to identify critical path and then figure out what are the techniques that you can use to reduce that critical path. And for adder design, what was the major problem for the critical path? Which part of the adder we had to optimize the most? What was the most troubling to us? Carry, that's right. So in this case, basically the game changes a little bit, because now we have equally important carry and sum bits, and then we have to optimize them both and eventually use different adder structures than we used for pure addition. So other possibilities besides this Wallace tree multiplier is basically to do a little bit more of sophisticated schemes for data encoding. So I'll just give you the idea of what's it about, and so you can basically revisit that in 241. So the problem that we have with this final adder is that we always have this carry rippling. And the carry rippling effect is caused when you have a long sequence of ones. So basically, let's take a look at the 8-bit number in binary format. So we have 0, 1, 1. So then we have another 3 zeros. And then we have a 0 again. So now this will basically create carry propagation through consecutive stages. So here's an idea, basically. Instead of representing this number in this form, so this is basically 2 to the 1 plus 2 to the 2, if this is bit position 1, this is 2, 3, 4, 5, 6, plus and so on, plus 2 to the 6. I'm going to say this is equivalent if I do basically 2 to the 7 minus 1. Right? So what I'm going to do is basically represent this number in equivalent form, and I'm going to use following notation. So I have my logic 0, and then I'm going to say this is my negative 1 at the least significant position, and then I have zeros, 1, 2, 3, 4, 5 zeros, and then I have finally 1 over here. And this is basically now reducing this critical path, but then you have to introduce more complexity to encode this negative number, and that's basically the idea that's used for further compressing this tree for large operands. So that's basically just playing with this redundant number system that you have basically 0 and 1, which is enough for the full number representation, but you also have this negative 1, which is redundant, but it helps you reduce the complexity of the implementation. So these are kind of the ideas that you may find in 241. Negative 1 is basically just has you no, this is actually so if you look only at this piece, right? If you look at this piece over here, right? So then you do this. Basically, you have 1 all zeros, and then you have this other 0. So from this number, you need to subtract minus 1 at this position. So another idea that you can use is now to say, well, this critical path is still too long. And another idea that I can use is basically insert the pipeline registers, do the technique of pipelining. And what pipelining means is basically choosing a cut set to insert the pipeline registers in the forward path. So you basically insert the register here, and you slice through all of these branches. So now that you basically, your critical path in terms of a clock cycle, which will be clear next week when we start talking about timing, is reduced. Because now, let's assume that you had, that it would take some time t to get the propagation delay from the input to the output. And now when you introduce pipeline register, let's assume that you put them somewhere in the middle. So what you're doing now is basically, if you have now propagation delay t before you can have new inputs, then you slice this through, basically. And then you have t over 2 here and t over 2 here. So as soon as you get past this register, basically you can start changing your inputs again. So this way you basically double your clock frequency, but you introduce one extra cycle of latency, what we call. So you have to wait one extra clock period to get your output result. And that's basically the idea of pipelining. And the multiplier is a good example to sort of understand all of these like system level issues that you may face in real designs. And that's about how much we are going to talk about multipliers. Any questions? All right. So now let's go to another arithmetic block over here, and let's talk about shifters. So shifters are sometimes very important blocks to have when you, for example, oftentimes you have to shift your word left or right by a certain number of bits. And this is particularly useful in the cases when you want to implement scalars, where you want to, for example, implement constant multipliers, when you need to multiply by a constant. For example, multiplication by 1/2 means just shifting the word to the right, right? So you basically just change your significant bit positions. And these units are, from that standpoint, very important. They are quite trivial, but also very important. So here's a basic idea. When you need to implement a shifter, so it is very simple. When you have, for example, fixed number of bits that you want to shift, that is basically just the rewiring bits, and that is really trivial. So nothing clever there. But now let's suppose that we have a little bit more complicated case when sometimes we want to have flexibility and say, let's have programmable shifters. So sometimes I want to shift from left to right, sometimes I want to shift from right to left, and sometimes I just like the word that I have. And that's the idea to look into these binary shifters that are shown here. So what I have over here is I have inputs A, and then I have outputs B. So they correspond to bit slices I and I minus 1. So over here, I can choose basically whether I want to stay with the value that I have, whether I want to shift right or I want to shift left. So now I have to choose from 3 available options. And which logic function is this, by the way? It is multiplexer, correct, because you're multiplexing several options onto the output. So let me try to get a pen here. So let's assume that you have no op. So in that case, you just basically propagate your bits to the output. Now, if you want to shift right, and shifting right is normally from MSB to LSB. That's what we call shift right, shifting to from more to the less significant bits. So this is basically just going this diagonal. So AI appears over here, and the previous bit appears over here because this transistor is on to propagate this guy. And if you want to shift left, you basically just reverse the order. And this is the idea behind this binary shifter. So you basically have all these control signals that selectively choose which of the inputs is going to propagate to the output. Okay? That's a buffer. That's a driver. Yeah. So now let's take a look into a case where we have 4-bit situation. And now let's assume that we need to implement a shift, programmable shift with 0, 1, 2, or 3 bits, because this was just a binary shift. Basically, we can go 1 bit left or right, but for most cases, that's not enough. And shown here is a structure that is a little bit complicated, so let me draw it here again in a little bit simpler form. So what we have over here is that we have all these horizontal signals that we have from bit slices. So this is A3, A2, A1, and A0. So now let's add vertical lines over here. So you have 4 of these vertical lines, and then finally let's have these buffers that will produce output signals. Maybe I can use this. Okay. So this is going to produce B3, Then going over here is B2. So B0. And now for the case where and let's make connections between this horizontal row and vertical row. So let's make this A3 also going down. Let's make this A2 going down. This would be A1 and A0. So now what I need to have is programmable switches, basically, that will connect certain values from the input over to the output. And for that, I'm using controlled transistors. So let's assume, for example, that I want to have shift to the right by 2 positions, and I want to connect A3 to this output. So what I have to do is then basically have a transistor here that will provide that connection. So I'm bringing in A3 over here and passing it to the output. So what I'm going to have is basically an array of switches. So I'm going to have transistors around here that will control the switching. One transistor here, here, and so on. Okay? So now let's assume that I don't want to do any shift. And in that case, what I have is basically just connect hardwire A's and B's. So in this case, I have this row of transistors turned on, and this means shift 0, right? So let's assume now that I want to have shift by 1 bit position to the right. So this means that I want to control basically A3 into B2 using this transistor. So now I also have A2 going into B1, and then I engage this diagonal, shift 1. So now the question is, what really happens with this A0? And for A0, you can have several cases. You can basically have a logic shift when you have a rotation. So basically you have A0 going back to the MSB, but for most arithmetic calculations, that's not really useful operation to do. So what you want to have is arithmetic shift. And arithmetic shift is basically you either have normally have zeros into the MSB. So when you're shifting away your word, you are padding with zeros. But over here, what we are going to do is basically repeat MSB for all of these positions. Okay? And what's going to happen then is basically this will become controlled by SH1. So B3 will be equal to SH1. So now sometimes MSB can be 0 or MSB can be 1. So we are shifting basically MSB. So why are we choosing to shift 1 as well as 0? 2's complement? Correct. So basically you have 2's complement numbers and you're just shifting MSBs for negative numbers. And this is basically the strategy that you have in this case. So then for shift by 2 bit positions, so there you have SH2, and then you have another signal over here, SH2, that helps take care of the MSB, and then finally you have shift by 3 bit positions, SH3 here. So this was no op over here, shift equal to 0. So then you're shifting here from to the right. Okay. So now what is good about this implementation from the speed perspective is that signal is selected by only one transmission gate. So you have only one resistance to worry about, right? But the trouble is that you have lots of capacitance from all these possible options. So which basically tells you that this is good, but from the performance perspective, it's not the greatest solution because it doesn't really scale well with the number of bits. So this is just 4 bits, and it was already complicated. Imagine having this matrix of pass transistor gates for 16 bits or so, or 32 bits, and then it will become really, really hard to implement. So another thing is that for each of these options, shifting 0, 1, 2, or 3, you have to have extra control wire. And if you have, again, 16 wires, then it's basically too much of a routing overhead. So now it will be interesting to see how we can basically reduce this complexity. So basically reduce the total capacitance that we have, and also do a little bit more clever implementation of this thing. So basically, let's say that we have to shift by 3. So basically, in binary format, that would be 0, 1, 1. If we shift by 2, 0, 1, 0. If we shift by 1, 0, 0, 1. So this is basically encoded format for this shift operation. And now, if you have control lines over here, what has to go between these two? What logic operation? Decoder? Right. Okay, so that's the idea that we are going to explore next. Okay, so let's go back to slides and show you an implementation of this thing. So this is basically clever implementation when you have really dense and compact layout. It is, however, dominated by all these wires, because when you see this is a transistor over here, then you have another transistor over here, and the rest is pretty much wiring. So you have all these control signals down here, input signals, and then you have the final buffer over here. So it's a 4x4 barrel shifter. So here's another idea. Instead of having all these different control signals to control every possibility that you may have, let's do this staged approach, because we realized that we had a problem with too much capacitance from a barrel shifter when you have every single combination hardwired to the input of this poor buffer that can't really drive all that capacitance and all these pass transistors. So here's an idea. Let me have a first stage where I can basically do either shift by 1 or no shift. So basically, when I'm no shift, I'm just propagating this signal through. When I'm shifting by 1, I just go down 1 bit position. And then in the second stage, I can either continue to propagate my signal through, or I'm basically going with a wire down 2 bit positions. And the same idea over here. So you're just basically going in a binary format, in a logarithmic form. You remember from adder analysis, we really like logarithmic dependencies where we are working with a large number of bits. So over here you can also continue, or you can basically bring a wire from the previous bit, go down 3-bit position through this multiplexer, and come to the output. So now this gives you an advantage because you can program your shift. So let's assume that you want to shift by, for example, 3-bit positions. So you basically engage control signal SH1 and SH2. So you do it in stages. So you shift by 1 and by 2, and you're done. So that's basically the idea. And this approach also, you see that this stage is very simple. Over here, you have to bring more and more wires across. And as you go toward the output, then you have increased routing complexity as well. So this scheme is also basically wire dominated. And that's the case in shifters, because if you want to explore all these different options, then you have to have all these wire tracks ready for your signals to travel through. And here's a layout implementation of this. Now you see basically the impact of wires. So let's label a couple transistors. So let's see, this is a transistor over here. So this is the area with transistors. This all area here, that's pure interconnect. So this is all wires. And this is basically a structure that is wire dominated. Okay. And before we go into analysis of power consumption, let me show you one more topic over here. So basically we can use this programmability type of thing for various other functions. And let's take a look into two's complement feature of binary numbers and see how we can implement a subtractor. Basically, adder is very important operation, multiplier is very important operation. So let's do the sub over here. So what we know is basically when we want to add two numbers, so here's an idea. So we basically do a minus b. So the way you implement this in binary format is you say a plus b complemented bitwise plus 1. So it seems we would be able to do this with adders if we program it right. So now the question is, it seems that you have to use two adders here, but to add all these numbers. And the question is, can we do this with one adder? How we can add this one? Where do we put this? Carry equal to 1, exactly. So that's the idea here. So basically what we do is, if we save, so this is an adder. So let's assume 1-bit case for simplicity. So basically if this is b, so this is inverted b, and we say carry is equal to 1. So this is a minus b, right? So now let's look into the case where we basically want to have programmable add or sub. So that's an idea. So basically when we have, let's see what happens with this. We would need to have some control signal, select signal, that will basically do either 0 or 1. So basically what we want is when the select signal is equal to 0, we want over here at this input we want b. So this is b in, b is equal b in. And when the select signal is equal to 1, we want b in to be equal bitwise complement. So this is now our add, and this is sub. So now what is, and we also want carry in this case equal to 0, and carry is equal to 1. So we basically feed this select signal into the carry. So now the question is, how do we implement this programmability, this signal be in? What would be appropriate logic function to do this? So basically when this one is 1, then you get inverted. XOR, great. So let's see what happens when we XOR these. So this is input B. So let's do XOR. So 0, 0, 0, 1, 1, 0, 1, 1. So what we have over here is then 0, 1, 1, 0. And now observe the following. So basically when we have S is equal to 1, so this is now S equal to 1, B in is equal to the complement of B. And when S is equal to 0, B in is equal to B simply. So now what we do is we can take this into an implementation, and then we can have this situation. So we basically have an adder. So we have input A. So we have S and B, and this is our carry. input, and this is now add sub. Okay. You can also exploit this idea to build comparators. If you, for example, add an extra inverter over here, then what you're going to get is basically the condition if A is greater than equal B bitwise. So this programmability comes in quite handy for implementation of other arithmetic operations. Any questions? Okay, so let's go into power consumption. So now this is an issue that we need to revisit, that we understand the logic level implementations of Boolean functions, so we can play more with this activity factor analysis. And this is basically the idea behind going back to the power in CMOS. But to give you a perspective, let's take a look at some interesting numbers. So there was a survey done a couple of years ago that concluded there is about 400 million computers, personal computers in the world, and totally they consume about 0.16 petawatt. So that's 10 to the 15 watts of power dissipation. And to provide all that power, you need about 26 nuclear plants to run all this computing in the world. And that is basically just for the personal computing. That's a huge amount of power. And another issue is when you have all these data centers, when you have all these air cooling fans and air conditioning that you basically can clearly see around the buildings. If you, for example, the cases that you have in Google or Yahoo, when you have a click of a button, that is basically a lot of power consumption behind that. And if you drive around the Silicon Valley and see a lot of like these fans stacked on top of each other around the building, that's probably the place where they have a lot of servers and they do a lot of computing, companies like that. So one single server rack is about 5 and 20 kilowatts, and then you have hundreds of those in a single room. And so that's basically hundreds times 20, so that is basically 2 megawatts. So now the question is really, how do you take away all that heat? So that's the big issue, really. Like at the processor level, you have all these like little heat sinks, and then in the room you have all these like air conditioners and cooling systems. And that's certainly a big challenge. That's why we need to really worry about power consumption. That has become the major limiting factor for technology scaling, and designs are no longer limited by the amount of functionality you can integrate, but rather power consumption. So here's an illustration of one of these fans in the server room, when you have all these racks and basically it blows air away from these machines, and these are just air cooling vents that take away all this hot air. And if you look also at the processor level plot from IBM, similar to the one that we saw a couple lectures ago, then you can clearly identify these very hot spots. And basically thermal density is really what is the problem here, power density and our ability to take away all that extra power. But this is only for high-end computing. When you have desktops and servers, the same case is very much in portable devices. So basically, now you're limited by battery capacity, and battery capacity doesn't scale with Moore's law. So it's basically battery is very limited. There has been a lot of improvements in battery design over the past 10 years with proliferation of these mobile devices. Over the past 10 years, battery capacity about doubled or increased about 4 times, but that's about it. And here's a road warrior of the future, when you have all of these extra functionality in your PDAs, then you have to carry very large battery, but that's not really the way it's going to happen. So what goes here is that the power constraints are different, because obviously you have much lower power limit over here, but the nature of the problem is much the same, because you have also power, density, and thermal dissipation. Over here, you can't really afford to have fans while you're talking on your phone. So there is a fan going around and taking all that extra heat. The phone first won't long last, and you don't want to carry bricks around, basically. So that's the reason why these phones have a small form factor, and they are basically determined by the capacity of these batteries. So the game here is you have certain capacity of a battery, and that's the limiting factor. Now you decide what you want to do with it. How much signal processing you can do, for example, with 3 watts. That's as much as you can have. And when you travel from one continent to another on like 10-hour flight, you still want to carry your laptop. The majority of weight is in batteries. So if you want to survive through the 10-hour flight, you maybe need 3 or 4 packs of batteries to do it. And that's basically the major limiting factor. That's why it's even more important to go after this low power design. And I guess this slide shows some progress in battery materials, and with the introduction of these lithium materials, there's been this increase over the past 10 years or so where you have batteries of higher capacity. But that's basically the game here. You have fixed amount of power, and then you have to design circuits to deal with that. Okay, so where does the power go? This is a standard story from couple lectures ago, so this is just going quickly to review that. So the major source of power consumption is basically still dynamic power for charging capacitances. That's dominant today, but with scaling of technology and more leakage, then we also have to worry about leaky transistors, and it is very much of a concern in desktop devices, but much more in portable devices when you have basically this low activity regime of operation when you're not using your phone, and then it just leaks away. And then short circuit and static power. So reviewing dynamic power consumption, here's a network, logic network. It has inputs over here, A, and it has this output capacitance, CL. So now the question is, how much energy do we need to spend really to provide some voltage and deliver charge onto this capacitance? And that is determined by this formula over here. You have to integrate power over time it takes to charge this up, and then you end up with this well-known expression CL VDD squared. So that is the total energy that is taken out of this supply voltage to charge this capacitance. So now you know that only half of that energy is basically stored on this capacitance, because the other half is dissipated as heat to a resistance, and that's shown here. So basically the total energy that you start from is this CL VDD squared. What happens during charging, half of that energy is dissipated as heat, and later for the discharge cycle the other half gets dumped through this pull-down network. So that is the basically charge and discharge cycle that we are familiar with. And if you want to calculate power, then you have to take that energy per transition and multiply by this transition rate. And transition rate is how often your output goes from 0 to 1, because that's where you're pulling CL VDD squared amount of energy out of your supply. What happens later for the 1-0 transition, that's also accounted for. But this is the total energy that you take out of your battery source, ultimately. And this can be expressed as the clock frequency times the probability of these 0 to 1 transitions at the output. And you can express this further as a switched capacitance times VDD squared. So basically your switched capacitance over here is equal to CL times P 0 to 1. So yeah, that's right here. And what this tells you really is that power dissipation is data dependent, because it depends on this switching probability. So now let's go back into logic families that we learned so far and see what are the good choices in terms of this switching probability and what are the bad choices, because we've analyzed static CMOS, we analyzed dynamic, this CVSL, which always basically switches from 0 to 1. So let's get some insight into what happens with our Boolean realization of a function using these different logic families, and see which logic families are more power hungry than others. So that's basically telling you the same story over here, that the average power can be calculated using this formula, and this is what we have already introduced. So it's basically, the point to focus on here is this alpha switching factor. And there is a number of factors that really affect this switching activity. So one is type of logic style that we are going to review, static versus dynamic. Type of logic function. Different logic functions have different activity rates, XORs, NANDs, NORs, and so on. Then you also have to worry about signal statistics. You may have, for example, a gate that switches, for example, a NAND gate that has a logic 0 1 out of 3 times, 1 out of 4 times, but then basically you have to take into account what is the switching probability of the inputs, because sometimes you may have very high probability of input switching, sometimes lower, so we have to consider that. And also there is inter-signal correlations. Basically, so far we assume that all signals are uncorrelated, but when you have reconvergent fan-outs, you have to worry about signal correlation, because they go through different paths, and the initial switching probability at the input propagates differently through these different logic networks. So that's what we want to analyze. Okay, so let's take a look at a 2-input NOR gate first and understand what kind of numbers do we get for this case. So if we do the truth table, 0, 1, 1, 0, 1, 1, and output is 1, 0, 0, 0. So now let's assume that signal switching probabilities for both inputs are equal. So P of A is equal to 1 is equal to 1/2. P of B is equal to 1, and we put this in a short form as PB is equal to 1/2. So basically what we are ultimately interested in is probability that output goes 0 to 1, right? This is equal to the probability of output being 1 times the probability of output equal to 0. Okay? So let's take a look and see what's the probability of output equal to 0 and output equal to 1. So let's first consider the case when output is equal to 1. So what is P1 equal to? So that's basically probability that A is equal to 0 times probability that B equals to 0, right? So now we have the probability that A is equal to 0, it is 1 minus PA, probability that A is equal to 1, times 1 minus PB. So that is equal to 1/2 times 1/2, 1/4. And in the same manner, you can derive probability of output being equal to 1 by taking all these combinations, or you can basically say output is equal to 1 when it's not equal to, output is equal to 0 when it's not equal to 1. So it is 3/4. So you multiply this together, 3/4, 1/4, and you get 3/16. Questions? So let's take into account XOR gate to see what's going to happen with XOR. So we have A, B, XOR 0, 0, 0, 1, 1, 0, 1, 1. And let's say also PA is equal to PB is equal to 1/2, then the probability of 0 to 1 is equal to P of out is equal to 0 times P out is equal to 1. So basically now we already know that this probability over here is 1/4. Likewise, this is 1/4. So basically this is 1/2, 1/2. So this is equal 1/4. So now compare this to our previous example when we had NOR function. So you see that the NOR has slightly lower switching probability than the XOR. And this is basically one of the trade-offs that you would like to see when you compare different logic functions. So now let's take a look into different logic implementations of the same function to see what are the other trade-offs that we have. So for that, let's go back to slides. So let's take as an example dynamic gate, where we have pre-charge evaluate function. And so basically the idea here is that power is dissipated only when previous output is equal to 0, because that is when you are going to pre-charge your output. And now, so for the dynamic gate, you have basically a different scenario. So let me write this down. So basically, for the general case of static families, you have P0 to 1 is equal P out is equal to 0 times P out is equal to 1. Now for dynamic, you have P0 to 1 is equal to P of output is equal to 0. So this is output O. So what this suggests you is that P0 to 1 dynamic is greater than P0 to 1 static. Okay. So let's go back to slides and do this two-input NOR gate. So in this case, if we also assume the same conditions, PA is equal to PB is equal to 1/2, then yes, so that's dynamic power consumption. So if we take into account the static case, so basically over here we have P out is equal to 0 times P out is equal to 1. That was the previous equation we established, and this is equal to 3/4. So in dynamic gate, you have this probability of 3/4 compared to the static case when we had 3/16. So that's basically the takeaway message here, that switching activity is always higher in dynamic gates.
Why P out equal 1? Like P out equal 1 equal 1. Like you have 3/4 times 1. Why 1?
This is because output always gets pulled up to 1 for during the pre-charge phase. But you should really use this formula. So this is rather confusing, I agree. So you can basically safely use this formula for the dynamic gates, knowing that you always have to pre-charge to 1. Okay. So let's take into account another logic family. So let's take into account this dynamic CVSL. So in this case, due to this differential nature, you basically have guaranteed transition from 0 to 1 for every operation. Because when you finish pre-charge in the evaluate mode, you will always have one branch that is pulling down. Another branch will stay high, and then for the next pre-charge, you pull them both up high. So this is basically alpha 0 to 1 is equal to 1. So let's add that over here. So we have DCBSL P0 to 1 is equal to 1. And you can't go higher than that. So from the power perspective, so this is good. This is worse, and this is bad. It's really bad. But there is also a trade-off in speed. This one is slower, this one is the best, and this one is used in special cases.
When you say that DCVSL is the worst case, but shouldn't we also consider that it produces complementary outputs, and if we had to achieve the same by using a static inverter, we would have had two stages or two parallel implementations, and that would have taken double the energy of what we consider as one stage?
That is correct. So the question is if in compare dynamic CVSL versus the static implementation, and then you basically have to replicate the hardware for static implementation to provide all this functionality. But then still, basically, you can't beat this alpha 01 is equal to 1, because we saw that for static implementations, you have like 1/4 or 3/16. So even if you double that, it's not going to add up so high in terms of switching probability. So now we are purely analyzing here the switching probability. When you need to implement certain function, then if you need complementary outputs, definitely that's a consideration you need to make. See how much total switching you need to dissipate to provide that extra functionality. It's a good point. Questions? Okay, so here's a problem. When you analyze all this by under the assumption that both inputs are independent, that is really not the case in practical examples. So let's take into account the case where we have reconvergent fan-out. So over here, I basically have this signal B that travels through this gate and shows up at the input of this gate and gets combined with itself. So what you need to do here is in order to calculate the probability at this node Z, you have to take these conditional probabilities, because Z would be equal to 1 when both inputs to the AND gate are equal to 1. So basically when input B is equal to 1, but also when X is equal to 1 under the condition that B is equal to 1, because B is also at the input of this X, and then you have to calculate conditional probability. And then, unless you're really into Boolean algebra, this becomes intractable really fast when you have complex structures. Imagine doing this for a carry look-ahead adder. That's going to be really, really difficult thing to do by hand. And here is an example. So let me work that example over here. So let's take into account this case. We have A, B, C, and then we have Z, or reconvergent fan-out. So we have input A, C, B, and Z. So what we have over here is that P of 0 to 1 is simply equal, and then you can derive this expression. I think I have it somewhere. You can derive this expression that basically for the AND gate you will have this situation that P0 to 1 will be equal 1 minus PA times PB times PA PB. But over here, it's more interesting case to consider. when we say that P of Z is equal to 1, that is basically equal to the probability of C equal 1 when B is equal to 1 times probability of B equal 1. So now clearly this is not possible, right? So this probability is equal to 0. And this is basically ill-conditioned case from the Boolean functionality perspective, but it is rather often used for in real-life implementation to create glitches at the output, because you take advantage of this propagation delay over here. So basically when you have this input equal to 1, or what's the way that works? So basically when you have, right, so when you have this 0, then this is 1. And then you transition this one basically, so if this is B, so B goes from 0 to 1, and then C goes from 1 to 0 after 1 gate delay. And during this time, Z is basically creating a pulse. So that's why this is used. But basically, the message here is that you really need to take into account these intersignal correlations and take into account their mutual dependencies when you deal with reconvergent fan-out networks. Question?
How would you account for the energy power loss due to this glitch? It don't show up on a probability.
That's a really good question. So basically the question is, how do you account for the energy lost during creation of this glitch, right? So that basically what you need to do is understand where is that glitch coming from. And what you would do basically for the first order analysis, let's say I would measure power consumption out of this gate, because that's the one that is providing switching transition at the output capacitance. And that's coming next, actually. That's a good introduction. So basically, this is a further illustration of the same concept that we just described. When you have the case where you have uneven arrival times of these signals at the input of a gate. So let's take into account this gate where basically inputs A, B, and C were at, so A was 1, B was 0, and C was 1. So now let's take into account the case where A goes 1 to 0 and C goes 1 to 0 at the same time, right? So what we have is that in this case, basically signal X will go to 1 after this gate delay propagation. And then it will basically take another, so this one becomes 1, this one becomes 0. So there will be a short period of time over here where basically we have, during this period of time, we have the case where C is equal to, so let's see what's the case, C is equal to 0. C is equal to 0, and also X is equal to 0, right? And then one gate delay after, you basically have this NOR gate is equal to 1, and then when you get this rising transition, you will have to wait for one gate delay to bring this down to 0. So this is basically what is called glitch power consumption. It's also called dynamic hazard, because you don't have anything beneficial in terms of logic functionality, but it just hurts you in power because you have uneven rival profiles. So there is a number of things that you really need to take into account. One is type of logic function that you want to implement. Number 2 is type of logic style that you want to choose for implementation of a given logic function. And number 3 is basically to figure out how do you implement this from the signal arrangement perspective, from the reconvergent fan-out, signal correlations, and also the arrival times. So this is basically what you need to care for in the power consumption. And I guess this also gives you more of the same. When you have this propagation through a chain of NOR gates, then you have basically all these intermediate signals going into transitions to create the final value. And so this is basically, we'll wrap this up next time, and we will go into sequential logic. So I'll see you later tonight.